we'll discuss one of the most pressing problems in physics and cosmology, quantum gravity. We'll be looking at the current state of knowledge on this problem, as well as some directions for future research. Spontaneous symmetry breaking in quantum field theory. The most significant and fundamental feature of quantum field theory is its spontaneous symmetry breaking, which occurs when a system that has been in an extremely symmetric state, where all the particles are exactly identical, becomes less symmetric. This phenomenon happens even in our universe, and it's one of the key ways we can explain why so many things around us look different from each other. The gravitational field as a Goldstone boson. The gravitational field is a Goldstone boson because it is not conserved. In other words, the total energy of the system can change if we add or remove one of these particles. The gravitational field couples to the Higgs field and gives rise to mass for fundamental particles, hence its non-conservation. A new kind of quantum spacetime. Quantum spacetime is emergent. This means that spacetime is not fundamental, but instead emerges from a more fundamental structure. It doesn't exist in its own right. It has to be put together from something else. This new kind of quantum field theory is not Lorentz invariant, which means that it isn't compatible with Einstein's special theory of relativity, or general relativity. However, this new quantum field theory does generalize the standard model by including fermions, like electrons, and bosons, like photons. In addition to being non-Lorentz invariant, it also contains two additional spatial dimensions, compared to our 4D spacetime. Time and space are intertwined in a single manifold called spacetime because they're inseparable. Directions for future research. The problem of quantum gravity is one of the most challenging in physics today. The issue is not simply one of reconciling general relativity with quantum mechanics, but also involves understanding how spacetime emerges from a background governed by relativistic quantum fields. This is a long-term goal that has yet to be achieved, and it will require an immense amount of theoretical and experimental work before it can be realized. If humanity were able to create a theory that successfully unifies general relativity and quantum field theory, QFT, then this would have far-reaching implications for our understanding of fundamental science, as well as our knowledge about nature itself. The problem of quantum gravity should be recast as an emergent gravity problem. The standard model of particle physics and general relativity are both well-tested theories that have been confirmed to the best current standard. But when you look at them from a distance, their differences become apparent. General relativity applies to large bodies like stars and planets, while the standard model is about small particles in space. If we want to create any model of reality that accounts for everything both large and small, we need a theory that merges these two approaches into one consistent framework. This is where loop quantum gravity comes in. Loop quantum gravity attempts to reconcile general relativity with quantum mechanics by finding some middle ground between them. In particular, it posits that spacetime itself emerges from smaller pieces called quantum processes, which have nothing to do with actual quanta. We have shown that quantum gravity is a problem of spontaneous symmetry breaking. This means that the fundamental laws of physics, including quantum field theory and general relativity, can be described in terms of an emergent gravitational force. Emergence in quantum gravity will not only help us to understand how space-time emerges from more fundamental physics, but also how matter particles might come out as well.